Yeah, this is causality. And so what we are going to do today is just like an introduction to what is a causal analysis. And if you're interested, you could go more into the details. I've introduced you some books that could be also very useful in case you're interested in this topic. So let me first motivate you by Democritus. He said that I would rather discover one cause than be the king of Persia. So, and just hope that I can convince you that this is not a very easy job to find a causal relationship. And I also like this example here. I don't remember who told me first this, that they had a professor discussing what is causal, what is just a correlation. And then he said that, yeah, I was once visiting in vacation with my wife, and then we saw some storks, and then my wife got pregnant. And so, yeah, after that, after 2 years, again, we visited the same location, we saw some storks, and then again, we saw our second boy came. So that's why I think storks cause babies to come. So that's what this is also another motivation. That's why this session is going to be important in arguing those kind of friends. That they believe that anything that you can see are coming from a causal relationship. This is another example. I got this from a website called Tyler Vigan. They have a book also. It's called Spurious Correlations. And there are many examples of like this. So for example, here you see that US spending on science and space and technology correlates 99% of the times with the amount of suicides. So if you believe this is a causal relationship, so in order to reduce the suicides, you should cut the spendings on science. So talking about causality has policy implications. So if you really believe that this is causing suicides, you must reduce the spending on the space. I like this book. I think I have it open somewhere. So this is there are like millions of examples here. So this is like the honey production bee colonies in the United States versus the nuclear weapons in Russia's stockpile. So if you all like here, the correlation is 98%. So if you want to, if you believe this is a causal relationship, in order to reduce Russia's nuclear stockpile, you should just remove all the honey producing bee colonies in US. There are many other examples here. Shark attacks with tornadoes and so on. What we're doing today, this is the last section of the book, and this is all about causal analysis. I'm just covering chapter 19 today, but the later chapters are very nicely follows what we are just introducing today. I guess if you had some econometrics course, you already know this Mastering Metrics book. This is a very standard book for econometrics. Joshua Angris just got the Nobel Prize last year. So this is a topic of a very important topic nowadays. And also, I really like the other guy, Judo Pearl. He's a computer scientist, and then he just realized that in the computer science, people don't care about causal analysis. That's why he initiated these movements of causal analysis science. And he has many books. These two books are the most famous ones. So he basically argues that the robots, how we can teach robots to think causal and not just correlations. And also have this other book, Causal Inferences. I have the link over that. So there's a link for it that you can see basically all the materials here. And for all of them, you can see like the Python, R, or Stata codes as well. So I'm going to also use what you see in the chapter 4 with some examples in today's session. Yeah, this is also a nice book. Okay, any questions so far?
So the book of Cunningham is openly available on the internet, or is it? Did you just Google it?
I'm not sure if it is like the whole book there, but I think, but just following this this website, I guess you get most of what you want.
Yeah, okay.
But it is like really very comprehensive here with all the codes and everything. Yeah. So what we are doing today, so we introduce first like some terminologies that you need. So something like intervention, treatment, subjects, outcomes. And then we dive into the treatment effects, how to measure them, and so on. And then I introduce you with causal maps. This is something that in econometrics, we don't use them that much, but in the causal science, people are using it a lot. And especially if you're in the middle of something econometrics and in the computer science, you're going to see them in the near future. So if you want to be a data scientist or something. And then there is this nice ladder of causality that is, I just got it from the book of Vi, this one. So this is the 3 steps that we follow in order to get something causal. So what you can see in the first step here, I guess you can also write, yeah, here. So this is only for all the robots and most of the machine learners that we have at the moment. They can only see the associations and correlations. So they never be able to discover something new, a causal relationship. Okay, so basically all the regressions you run is also the same. So you cannot say that I found something causal just by regressing something or by just having some machine learning algorithm that show me this. Okay, so yeah, most of the animals as well as these robots, they can just see the association. So if this goes, that follows. That's it. Okay. One step further is the ability to intervene in the nature. So, for example, a small child can, for example, yeah, not only can see what's happening there, but also can experiment something. So, for example, it can touch fire and see what will follow the fire. But still, he cannot assume that he found a causal relationship, because for causality, you need something called counterfactuals. And counterfactuals basically, so assume that you are in a parallel world. So in one world, something happens and the other doesn't happen. And then you can see in both of the worlds what will be the effect of the things that happened. So for this, you need imagination. That's something that only us could do that. But there is a huge initiation also in many companies, like Microsoft has a big research lab on that. So they're trying to teach AI to have imagination. And also in econometrics, if you're interested, Guido Imbens, who also got the Nobel Prize this year with his wife Susanati, they are working on this kind of thing. So to creating counterfactuals or models to create counterfactuals with AI. But yeah, we are still not doing that very often. Good. So any question here?
What is actually the definition of a counterfactual?
I'm just coming to that, so basically, so I'll show you exactly with examples how they can create counterfactuals. But
the basic is a thought experiment, yeah, about in hypothetical world.
Exactly, like what would have been if this didn't happen.
Yeah.
Exactly. Yeah. So let's have some terminologies. So what is intervention, or in the medical language, they call it treatment. So there are decisions and actions that aim to change the behavior or situation of some people, firms, and other subjects. Okay. So for example, if you pass a law, it is kind of an intervention, and so on. So for example, in the business environment, when you see some advertisings, changing in the prices, changing product display, or implementing some business practices or processes, there are all some interventions that will change the behavior of the subjects. And for example, in the policy is also like implementing laws and regulations, changing taxes or benefits, introducing specific programs that aims to improve the situation of some people. Okay, they are all interventions in the nature, and they will have some consequences.
I think the most prominent treatment comes from the pharmaceutical industry. Yeah, you have a new pharmacy, yeah, and you give to 50% of the people the real pharmacy, yeah, with the right ingredient, yeah, and the others get only placebos. Yeah, it's the same pill, it looks the same, but there was no content in it. Yeah? And of course, some are treated, and some received no treatment. Yeah, they just think that they eat a pill.
Exactly. Yeah. So that's basically like most of these things are coming from the pharmaceutical industry at the end. That they want to see the causal effect of their new pills or the new treatment, and I have also examples on that in the later slides. So who are the subjects? Subjects are those who've been affected or could potentially be affected in an experiment. So for example, when you go to a website and you suddenly see something like this most popular tag on some of the cases, it could be that website is doing an experiment here and just showing to randomly some people for this tag, and to other people don't show this tag, and then they want to see what is the effect of showing such a thing, or some angle or whatever. Okay, and if you are among those people who see this, you're among the treated subjects, and if you're among those people that don't see this treatment, you're among untreated subjects, but you are still both subjects. So because all the people who are visiting this website are subjects for this study. Okay, clear? Good. And then the most interesting thing is the outcome. So you usually do a treatment or intervention in order to change some outcomes. And the outcome variables, there are just some variables that could be affected by the intervention. So for example, if this is the revenue of the company or the number of people who get the subscription and so on. Just some outcome variables may be explicitly targeted by the intervention. So for example, the goal of the intervention is to induce the change in them directly, or indirectly, some other variables may be just be unintentional consequences of the interventions. Okay, so for example, you want to increase the number of subscriptions, but at the same time, you maybe got less user interactions into the website or something like that. Okay, this is direct and indirect effects. Do you still hear me? Because I guess.
Yes, wonderful.
Yeah, but I guess I need to change this because I don't have enough battery on me. How about now?
It's same quality, different acoustics.
Okay, nice. Yeah. So.
Okay, it's a bit louder, but that's fine. Go ahead.
Maybe my microphone is not. But the microphone should be. Yeah, I don't know. Okay. So yeah, in contrast to the outcome variable is the causal variable, which we show it with the X. So it is like the treatment or the causal variable that indicates the intervention actually. So it is most of the time a binary. So for example, either you're treated or not. So either you're under the surgery or not, either you got the pill or not. And but it could be also a quantitative value and a continuous value. So for example, like a discount. So you add additional discount for a treated group, and this discount could be any number. Could be a variable, basically. Yeah, but for all the examples in this lecture, we are just assuming we have a binary treatment for just the simplicity. And then, yeah, so we are going to introduce what is counterfactuals. So assume that we have a dummy treatment. So each subject in our study is either being treated or not. So if he was being treated, we show his outcome as YI1. If he's being not treated, the outcome should be this. Okay. But the problem is that in the real world, you are either being treated or not being treated. Okay. So there is a hypothetical outcome or a potential outcome there for each case. Okay. So if you're so if D is equal to 1, so if you are being actually among the treated guys, so your actual Y that observed is Y1, and the counterfactual of you is you in a parallel world just not getting that. Okay, but this is something that you won't observe here. And if you're not among the treated guys, then you're observed a U0, Y0, but the counterfactual would be the same guy with the same properties, just in a parallel world with who received this guy, this treatment. Okay. So yeah, so this unobservable outcome of each person would be a counterfactual of the guy. And the way to define counterfactual is that what could have been observed had the subject experienced what did not happen.
So
okay?
if we observe, yeah, well, the treatment may be an Amazon recommendation, yeah, like the one that you saw, yeah. And if we observe that people that get this recommendation are more likely to buy, yeah, then the buying probability is higher, and then we see there was a treatment effect, and basically if the probability of buying jumps from 0.5 to 0.8, yeah, and you have a 30% increase in buying probability. And then basically you would say the counterfactual for the treated is if they would not have been treated, yeah, they behave like the others, yeah, so they would buy with 50% probability, and the counterfactual for the non-treated is if they would have been treated, they would also have been buying with 80% probability.
Yes, exactly.
Yeah, and this counterfactual or this assumption is valid if and only if we randomly treat the people, yeah, such that there is no other explanation possible, and we have enough observations, basically.
Yeah, you're right. Exactly. So you're just 2 slides ahead of me.
Oh, okay.
So,
I never understood this really.
So let's see if I can convince you something today. So yeah, just what is counterfactual? So you know theoretically now what is counterfactual, but what it is in the real world, I will show it after this slide. So this slide is just another definition that we call treatment effect. So is basically the difference between the counterfactual of being not being treated minus what is actually the outcome of being treated. Okay, so in either cases, for each individual eye, we observe either this one or the other one. So that's the thing, that's the dilemma that you just mentioned. We can never see both of these things for any individual at the same time. But there are techniques that you can assume that, yeah, this should be this number for this guy. Okay. And another terminology is that, so basically a treatment has an effect if we can statistically can show that this treatment effect that we find here is different from zero. So it is either positive or negative. So then we can show that our treatment has an effect. Okay. And also another terminology is the homogeneity of the treatment effect. So this is basically ask if the treatment effect is the same among all the subjects. Okay. So if it is not, we call that it has a heterogeneous effect on the subjects. So let me start with yeah, we have still things to introduce. Yeah, there is something. So yeah, after we can measure the treatment effect. Usually people ask you what is the average treatment effect. So you have the treatment effect on all your subjects and you basically take an average of them. And then you call them average treatment effect, or ATE, which is basically the average of these treatment effects. So yeah, so it's basically the expected value of like the treatment effects. Okay. But yeah, when you see an expected value in mathematics language, it means that you cannot easily measure such a thing. So it's like you need to have a lot of assumptions in the real world. Yeah, so yeah, usually, yeah, when people call ATE, they refer to the effect of the intervention. So this is basically the first time you can actually say that, yeah, I measured something, the effect of something. And then, yeah, but the problem with the ATE is that usually it doesn't tell you anything about the distribution or this homogeneity of this treatment effect. And then there are some subsets of this treatment effect. So for example, you can do the same average treatment effect for those people who are targeted and people who are not targeted. So you could say average treatment effect for the treated group and average treatment effect for untreated group. So basically, yeah, just averaging averaging of this treatment effect here for the group of treated or the group of not treated. Okay, we can do all of them in one example here, and that's why I need you guys to tell me here what would be the ATE. Here we have 10 patients. So they have two choices. So they either get a chemotherapy, which is basically no intervention, or they got a surgery, which is the intervention here. Okay, so this is our Y1 is for those who got the surgery, and Y0 or for people who got the only chemotherapy. Okay, and then here assume that we have a parallel world. In one world, all the state patients got treated, so that's why we can measure this, how many years after the treatment they are living. And in the other world, they all not get treated, and then this is the outcome of the other world, okay? And then the difference here is the treatment effect. which is in this case is 6 years, because if the guy got the surgery, he will live 7 years after that, otherwise only 1 year. So the treatment effect for this patient would be 6 years. Okay. Yeah. So any idea how to do the ATE here?
It's just the average of the deltas, isn't it?
Exactly. Yeah. So, but we need the numbers because it's going to be.
But that's of course a data situation that we usually don't have. Yeah?
Exactly. That's the real world. So that's why I wrote the ideal world. Yeah. And I show you in ideal world what will happen.
So here we basically know the counterfactual for sure.
Exactly. Yeah. So one way to think about this would be like you have 10 pairs of twins that they got the same cancer in the same age. And then we can randomly just treat one of these pairs, and then we see the twins, 10 twins, and then we can see one live 7 years and one live 1 year, and so on. This is something that people do in actual economic research. So, for example, for the health economics, we had the course. Basically, there you always find twins, identical twins, that they got different problems, and then randomly some of them got the treatment and so on. And there you can see actually such a data set. But yeah, doing this kind of treatments is either unethical or it's like not possible at all. And that's why you don't see such a data set in the real world. Yeah, anyway, let's see the ATE here. So 6 minus 1 plus 4, let me do my calculations. If any of you also do that, I would appreciate.
I think it's 6, maybe the sum of all, I think.
Sum of all 6 divided by 10, so yeah. So ATE would be 6 divided by 10, just 0.6. Okay, nice. And so based on this ATE, would you suggest a surgery? So
probably yes, because it's above 0.
Exactly. So you find an average treatment effect to be positive. So why not? So you found a positive causal relationship here between being surgery and having more expected life. So you would recommend the surgery here. And by the way, do you do that for everyone?
With the assumption because we can't differentiate, that the effect is homogeneous. If we can form subgroups with additional observable variables, then of course we would try not to treat number 7.
Yeah, exactly. That's the thing. That's why the concept of homogeneous treatment effect is important. Is it homogeneous among? So if we can believe basically this 0.6 is going to be true for everyone or just for some people? Because as you see here, we get sometimes negative numbers. So basically treatment has a negative effect for these people. And yeah, that's why in the real world, you won't get such a data set. You usually get a data set after some doctors decided treat or not treat some people. And this is basically what you get here. So this is the real world data. So there was a doctor behind the scene and decided to treat this guy, but not treat this guy. So this guy being treated would have just 1 year of life expectancy. And that's why this is the data set that you see in the real world. Okay. So again, my question is here, how we can do the ATE.
Maybe compare average of all treated to the average of all untreated as the effect of living years.
That's a nice start. Let's do that. So let's basically just do the average of all these ones and the average of all these zeros. Can you do that now?
Right, 7 for the ones.
Okay, 7 for the ones. And how many ones we have? 1, 2, 3, 4, 5. Okay.
I think it was 35 by 5, and the result was 7.
35. So, okay.
It's 35 divided by, yeah, and the other is 37 divided by 5. No, 37.
What is it?
It's also 37, I think.
37. Okay. Which is
0.4.
minus 0.4.
Exactly.
Okay. Now you see that the treatment effect you found is negative. So, the real data set of what could happen showing you a negative effect of surgery. So what should we do?
Don't rely on the results because they are biased.
Yeah.
Because we don't know the life expectancy in absence of treatment. So we don't measure a real treatment effect.
Yeah, very, very nice. That's exactly, so what we did, we called that SDO. So it is basically a simple difference of the outcomes. So this is, yeah, this is an estimate for ATE, basically. So it's not exactly ATE, so it's just an estimate. Yeah, you can just basically say, yeah, okay, I just get the average for the treated minus the average for not treated. And yeah, the formula is exactly like this. So you get the average minus the average. What we exactly did now.
Yeah, but I think we would conclude that this is the treatment effect only if we know that the treatment has been random.
Yeah, exactly.
If we know that only almost dead people receive treatment, yeah, then of course the treatment effect is completely different.
Exactly. That's why if you just open this formula that we found, we can just rearrange the terms here, and we get the treatment effect that we actually want here, plus a bias term. So what we found is like this minus 0.4 that we found is exactly the 0.6, which is the actual real one, plus an error. And this error is only due to our selection bias. So yeah, so this SDO that we had is not working when we have some bias in the selection. Okay, and how we can get rid of bias? That's maybe the most natural question to ask. Yeah, so in order to use SDO, or basically the simple difference of outcomes, and then call it ATE, is to just make sure that we have an independence assumptions. In other words, we should make sure that being treated and not being treated, the outcome shouldn't be related to our selection of this D. So this treatment shouldn't have any assumptions basically on the population that got treated or not. Okay, so how we can assume we have an independence? There are some ways that people can do. For example, you can do a random assignment, just saying that, yeah, we sort people on alphabet, people with A, B, C, D get the treatment, otherwise not.
I actually think that this is not at all random. because for sure there's a names distribution that some names occur more often than the others, and this would only be random if we assume that across all age groups, basically the names are distributed equally across all letters or all starting letters, which is, I think, a very strong assumption.
Yes. Well, basically, if you attend one of our finance seminars, you get the same discussion always. So some people come with a random assignment, and we got a paper on that and showing that I found the causal relationship. And for 1 hour, there is a huge discussion. No, this is not because of that. So this is exactly what you can expect in an academic world. Yeah, yeah, you're right. I cannot argue with that. But just want to give you an example of how random things work. You can rely on the nature to do some experiments for you. For example, if nature gives you some earthquakes randomly in some cities and destroy their surgery rooms, then you can see that, yeah, then there is a natural experiment here that without our choice, we did some interventions. So we basically don't treat some people on those places that earthquakes happened. Okay. This is something people call natural experiments. Sometimes, yeah, you don't have nature to give you this kind of shocks, but people still can do some quasi-natural experiments. And this pseudo-natural experiments are usually like regulations that comes to states. For example, yeah, some states randomly decide to ban surgery in their states. So you have data for the whole US hospitals, and then you suddenly see, yeah, for example, New York and California, they want to ban the surgery, and then you can see the effects, the change in these two states, and compare them with the states that it's still doing. Okay, are you fine with these definitions? Yeah, there's also ways to create counterfactuals. So as I said, there are like econometricians that work on this, and there are some standard methods that you can find some synthetic counterfactuals. If we go back into this data set that we have here, so in addition to just being treated or not, we know some other factors usually about the people. So for example, we know the age, we know the backgrounds, we know their education, and many other things. Okay, and then we can use this information here to say, okay, let's find the most similar guy to this guy, and we go to the whole sample, and we suddenly see, for example, this guy is the most similar guy to patient 1. So then we can create a counterfactual like this. Then, yeah, we got a 7 year here, Y1, and Y0, which is also 7 here. Then reduce this. And so on. So this is like one way we call this matching. There are many other ways to do this kind of things. Okay, so yeah, if you're interested into this, chapter 21 of the book is basically doing this. Okay, you can do that yourself. Any questions here? Okay. So now I'm going to talk about causal maps. This is something that's very famous among those people that do the causal science, not necessarily econometricians. They are also called DAGs, so they are directed acyclic graphs. And then what they do is basically they have some variables like the X, Y, and Z, and so on. And then they show with some arrows the causal links between these variables. So people do that to just get an understanding about their big data sets. Okay, and then what need to be controlled and what don't need to be controlled and something like that. So you can always summarize the assumptions about the variables and how they interact to each other with these causal maps. And this is just a simple example here, that we are interested to see what is the causal relation of x and y. Is it negative, 0, or positive? And we know other variables also affecting y. They're called z. Okay.
But so isn't it is basically a subjective opinion about the guy who writes down this causal map? Yeah, because if you discuss this with econometricians, they may say, yeah, we don't know whether it's only one direction, yeah, maybe both directions, and almost everything, yeah, could have at least indirect back loops, making causality run from both sides to the other.
Exactly, yeah. So that's why for creating this causal map, you usually need a domain knowledge, or you need to assume the literature is correct somewhere. So yeah, you rely on the other people's findings usually, or you can directly show something already. That's why you can create the bigger causal maps. So just some other terminologies about the causal maps. So we have different types of variables, and we can divide them to endogenous variables and exogenous variables. Endogenous variables here, like Z2, they are those variables that at the same time affect X and Y. Okay, and they are basically a link between X and Y always. And they are different kinds. I'm just going to show you. And yeah, they're called also confounders. And yeah, so they're basically endogenous. They have some endogenous variation for X and Y. On the other hand, we have some variables called exogenous. So they basically only affect X, not Y. Okay. And these exogenous variables are very important for us because they can help us to find the causal relationships in the cases that there's a mess of everything affecting everything else. So it's one exogenous variable can help us to just establish the causality link between X and Y. Okay, and yeah, just going to show you how. Any question here on the terminology?
Is there what? There was Z1 and Z2. Is it both equal to Z? No. It's different.
There are different variables. Yeah. Just yeah. Z1 is an example of exogenous, and Z2 is an example of endogenous variables.
My understanding of endogeneity is that it is affected by something else. Yeah, so X and Y would be endogenous.
I think
Z endogenous, like Z2 is endogenous because it drives both X and Y.
At least the definition that I found in the book is like this. Yeah. So the variable is endogenous if affects at the same time X and Y.
Yeah. Yeah,
so otherwise, some people they call it the source of endogeneity, but you are right. So this is like
that's not the wording that we use in economics.
Exactly. We usually say X is endogenous because there is a source of endogeneity, which is the two affecting X and Y at the same time. So this is like the language that we use, but I find it somehow very similar still. We can just say the source of exogeneity or source of endogeneity. Yeah. Here is just one example for you. So the book has a data set on many observations that you see here. And here at the end, they want to see, do fruits and veggies affect blood pressure? They want to ask this question. And then, you see a jungle of causal relations here. Yeah, let's group them to exogenous and endogenous variables. Do you see any exogenous variation here?
Well, only healthy lifestyle is unrelated to fruits.
No. You mean this
No.
one?
No, it's not. Of course,
No,
false
no.
consciousness. Basically, everything depends on everything. Yeah.
No, but there is one exogenous variable here.
Taste.
Taste, yeah.
Yeah.
Yeah, here. So this taste is exogenous because there is nothing that affects taste, and taste directly only affect our X here and nothing else. Okay, so this is, yeah, for econometricians, it's a gold that you just found. And then, yeah, you can use taste to find the causal relationship in this data set. But now we just want to make sure that we got the terminologies right. So let's start with the other things that we found. So there's a feedback loop here in the doctor's advice. So as you see here, basically blood pressure can affect a doctor advice, and the doctor advice can affect using having more fruits and vegetables. And that's why the doctor's advice is causing a reverse causality here. So basically, so so if we don't have any taste and we just had the doctor advice and we look at this database, then we can see that the fruit veggies consumption is mechanically driven by doctor advice, which is mechanically driven by the blood pressure. So we cannot say anything about the consumption of fruits and the blood pressure just by looking at the doctor advice. Okay.
I have a question. Why healthy lifestyle has minus towards blood pressure? What does that mean?
So if you have a healthy lifestyle, you probably have a lower blood pressure, no?
Yeah. Then yeah, thanks. Yeah.
The other variable that is interesting here is socioeconomic status. It at the same time affects the fruit and veggies consumptions. Also, it affects the health consciousness, and health consciousness exactly again increase mechanically the fruit and veggies consumptions. And they're, like as I said, they're all endogenous, full of endogeneity here. Everything affects everything. And if you want to really test if fruits and veggies are going to increase the blood pressure or decrease, you just need to redefine this fruit and veggies, something that I guess in your econometrics course you call this 2SLS approach. So we call this, one way of doing that is just to call this an instrumental variable or IV. Then you redefine the fruits and veggies based on this IV variables to here. So it's always a function of this, right? So then what you can do is like just redefine this fruit and veggies in a way that you just remove everything else here. Okay. And then you can just basically see if the relationship exists or not. But this is something out of the scope of today's session. But if you're interested, I guess, I don't know how much econometrics you usually have in your master program, but this is called instrumental variables.
I can really recommend the Mastering Metrics book. It has lots of references to a Karate Kid, and it's actually quite fun to read.
Yeah. Causality is really fun to read. So as I said, like the storks and babies are just one example. There are many ways to just see the how the causality is important in our life. Okay. Any other questions regarding this causal map here? So what computer scientists do, they usually use these causal maps in order to just discover new causal relationships. So this is something that, for example, if you're interested to see how computer scientists do that, you should read the book of Y that I just introduced. But econometricians, what we do is just the IV approach. So we use it as an IV and do the 2SLS and so on. Okay, so now that I hope you understand what is co-founder, so let's see different types of co-founders. Okay, there are some co-founders that at the same time affect X and Y. So they affect X and Y, and I just want to see if you can find any common cause co-founder in this map here. So just for again, just to make sure you understood, the common cause co-founder is a variable that affect Y and X at the same time. Okay.
So we just look for nodes where more than one error is starting from, like health consciousness.
Exactly.
And also socioeconomic status.
Exactly. Social. So this. If you want to see what's going on here, this will be a co-founder for us because basically it affects both. It's a common cause co-founder, so it both affect to our Y here in this case and our X here.
I think terminology is the most difficult thing here, because when you use endogenous in a different way than you use in economics, and when we introduce the confounder variable, in economics we usually talk about factors affecting outcome. So this is a factor that affects more than two outcomes.
The good thing here is using these causal links is always a straightforward what to control in our regressions and what not to control. And that's why it helps to just look at this way as well to the data set that you have. And these types are important here because there are sometimes that you must control for something and must not control for some other things. And that's why these different things are important here. There are, as I said, there are different types. For example, there is a mechanism of reverse causality. If a confounder affect X and then X affect Y and then Y affect confounder again. So if we found a feedback loop like this, then we have a reverse causality. I mean, one example of reverse causality is nowadays very famous. And so you have the ESG here. So a company being very green or something like that, and then their stock return. So the stock return. And usually there's a confounder here, like there's a good manager. So, you could also have, let me give you a better example. Or like good accounting as well. Good accounting numbers. So when you have good numbers, good accounting numbers, it can make you richer. That's why you feel easier to invest on your ESG or greenness and so on. And at the same time, you see that when the stock returns are good, the company become even richer and then can do more ESG, something like that. And then it makes it difficult to see if it is really ESG that produce the stock returns or not.
Yeah, but it's a bad example because stock returns do not drive P&L, but rather the other way around. P&L should drive stock returns.
Yeah, I agree. Yeah, I don't know if I can find a better example here.
A good example for reverse causality is in general total sales and marketing spending, because you can, but they don't have a confounder, but you can argue that basically if you have higher marketing spending, you also get more sales, but also if you make a lot of sales, you have a lot of free budget and hence can spend more on marketing, which again drives sales. So
what is your X and Y here?
I mean, you can basically switch it. You can formulate the marketing spending as a function of total revenue. So if you have a lot of spending,
so marketing spending, and then,
or perhaps now do budget as Y, and then marketing spending as confounder, because then you have, when you have a lot of total revenue, you also have high budget, and from high budget you can basically invest a lot in marketing spending, which again drive your total revenue.
So some budgets here and then marketing spending.
Yeah, this should work.
Exactly. Which budget you have here again?
Yeah, I mean cash.
Okay.
Basically cash you can invest. If you...
Okay. Yeah, total revenues increase your cash, and then with more cash you have more marketing expenditures, and then it increases your total revenues again. Exactly.
Yeah, I came up with another example. So for example, we assume that drinking coffee makes people nervous, but it's actually the other way around. It's nervous people drink more coffee. So we just misinterpreted the model, and it's reverse causality. So people are nervous in the first place, and they drink coffee because of that, and not that coffee causes people to.
But where's the co-founder here?
Good question. For example, we can say that some people are prone to drink more coffee, so it will affect both.
No, that's not an example. No, that's wrong. Something that should be mechanically driven by this. So, for example, well, it's not that easy to find examples here, but yeah, reverse causality is always around us. What is most difficult, I guess, to find an example for is tree, like this one. This something that we call unwanted mechanism. That there is. So usually we are interested in this mechanism. So what is this? The causal link here, but there is an alternative explanation that goes on this way, and we don't like that. And that's why we call them unwanted mechanism co-founders. So for this one, you should think of something that has one direct effect and one indirect effect on the Y. And not sure if we can.
You could use X as a socioeconomic status, Y income, and co-founder education. Because you can basically argue people with a high socioeconomic status are usually highly educated, and when you have a higher education, you also earn a lot of money. But there's probably also a direct link of socioeconomic status to wage. When your parents are well connected, can give you a good job, you get a high income.
Exactly. That's also a nice example. Exactly. Yeah. So.
I also wanted to add, I think in regression analysis, as last example, like this co-founder is sometimes called a mediator variable. And in the first example, it's a moderator variable because it affects the relationships between.
Exactly. Sometimes you have a moderator of variables that you have first something here, and then from here you go to Y. That's if your causal link is something like that, you call it moderator. It's not co-founder. So there's there's another terminology here. So moderator variable is just here. But so what Philip just said is exactly So if it is like this moderator variable is like the connections here, the parental connections and something like that, and then this social economy status can affect one way like this, and the other way is just by having more education. You can have your causal maps also like this. Okay. Any more comments here or questions?
I think another example could be, is it like grades and then the happiness, X and Y? So the higher grades you have, the more happy you are, but the co-founder would be like self-esteem, because grades make your self-esteem higher, and the higher your self-esteem is, the happier you feel, something like that.
Yeah, exactly. So if you want to see it, do grades contribute to happiness? If that is your question, you need to take care of the self-esteem as well. So that's the way. The reason we actually introduce the confounders is that so when you want to do causal analysis, for example, in your regression, if you see any confounder, you must basically control for them in your regression. Okay, and that's why we introduce these confounders. Some of these confounders, like the self-esteem, is not available easily. Okay, and that's why in the real world we have so much difficulties to prove causalities. Okay, because if there is a confounder, you must control for that, but these confounders are not always available in your data set. Okay, hope you get how difficult it is. Yeah, that's exactly what I said. So you usually need when you want to talk about causality, you need to have one exogenous source of variation in X. Okay, you have two options to do that. So one is just doing experiments. As I said, you just control, you have a control and a treatment group, and then it's up to you how to affect X. And then the X has an exogenous source of variation, and then you can just check if this link exists or not. Okay. The other way is to basically condition on confounders, and in the regression setting, you can just think of having a regression on something, and this is your X, plus there are some other confounding that this ZI things. So all these Z's that are confounders that must be controlled for in your regression, and then you can see if this beta is positive or negative, and then you can claim that you have a causal relationship. Okay. And so there's one term that people usually say here. So we usually say a ceteris paribus analysis. So this means that everything being the same, what would be the change in X? So basically, if you can control everything that can affect X, so you basically make sure that like the two patients are the same in their age, their genetic backgrounds, and so on. And then you can see that if the X has an effect on Y or not. Okay. That's the motivation why we introduce confounders, and why we must always control for them. But the question is how easy it is. The answer is obviously not that easy, because in the real world you have always some omitted variables. So, for example, this in the previous example, the self-esteem is something that we cannot measure easily. And so the confounders that we want to condition are most of the time latent variables or unobservable variables, unmeasurable variables. And the real data rarely includes variables that measure all of the confounders. And the variables in the real data are often imperfect measures of the latent variables. So basically something that we call a proxy variable. So usually we call similar variables and we say that this is a proxy for these confounders that we have in mind. And when you fail to condition on some of the confounders, they call that you have omitted variable bias. And it's biased the estimated value of the effect. Okay. Any question here? Okay. Okay. Now that you know that you need to always control for confounders, there are examples that you shouldn't condition on. So they are not calling confounders anymore. This kind of examples that you see here, they are called bad conditioner. And bad conditioners include the exogenous source of variation. So if you have an exogenous source of variation in your regression, you shouldn't condition on that. Okay. One example here, let me show you here. So for example, this could be a sunny weather. And this is like the tone of managers in the earning call. And then here is the stock price. Okay. If you want to find the if tone affects the stock price, so if the managers are more positive in their speaking, they cause the stock price to go upper. If you want to answer such a question, you need the source of variation. You can see later how we can do that, but for sure you cannot regress y on x plus z. If this is it. This is not allowed. So this will kill all the effect of x. Okay, you never should do that. The other bad conditioner would be a mechanism variable. So if you know that your x is affecting y through a mechanism, you shouldn't control for this mechanism here. Okay, because conditioning on this variable will kill the effect that you are interested in. And the next example would be the collider variable. That is something.
Short question. With mechanism, you mean perfect multicollinearity, basically. So, for example, size in square meters and inch or something, because you can translate one into the other based on a formula. Or what do you mean by mechanism?
Yeah, so could be also multicollinearity, but basically, if you know that the x is connected to y through this variable, conditioning on this variable will kill lots of information that exists in x. So if in your, so this is the z and this is the x and this is the y, this regression will give you a 0 beta 1, because all the information exists here, and this will be a significant variable here, but this should be 0.
Yeah, but if x has no impact on y, we can just leave it out and just use the bad conditioner variable, right?
Not sure if I get you correctly. We are interested in this, in both of this effect.
Okay, yeah, okay.
So we want to see, so ideally we want to have the true B1 here. And then if we condition on Z, this is not a true value anymore, because part of this relationship is being consumed by the Z. Okay.
Oh, but there are some techniques to find this relation, isn't it? Like we could regress X on bad conditioner and then X and Y, I think, and then separate the part of variation from of bad conditioner from the variation from X to Y to find this real connection of X and Y.
Yeah, but why you make the world so difficult? So you don't basically you just need, so if you have such a relationship here and there's no other complexity, if you only have this, you have X properly measured and Y properly measured, you can just regress Y and X. You don't need anything else here. And then what you find here is just a causal link.
But this will be wrong.
But but also may be wrong.
Yeah, if you regress X on Y in this case, you will capture some of the variation that is contained in bad conditional, or that some of the causal impact bad conditioner has on Y, and your coefficient for X will be biased.
So the question is, does X affect Y? And you are not interested in through which mechanism is affecting that. So this is a consequent question. So first you need to ask if X explain Y. This is the first question. And second, if you could establish this causal relationship here, then you can go and say, yeah, it is going through this mechanism. And then you can control this mechanism and see if you control for this, and then the beta 1 here is insignificant. So you can say, yeah, this is through this mechanism.
Okay. Yeah.
Okay.
This is
that makes sense.
Exactly. That's how you do the analysis usually. Yeah. Usually, like if you read, if you're interested in causality, I think economics literature are the best way to see how it works in practice. Because like most of the papers, they're like this. So they found a relationship and then they go through, maybe it's through this mechanism. So just testing this and then testing that and so on. And yeah, that's basically how they write papers. Yeah.
There are also a lot of really bad papers out there with an
I have a
research
slide.
design.
I have a slide on that. And like the collider at the end. So here, so the collider here is like an interesting case because, we should always find colliders to make sure that we don't go into the trap of confinders. So most of the times people control for the colliders that shouldn't exist because Y is affecting that, yes, X is affecting that, yes, but it is not a cofounder. So the difference between cofounders and collider is that, so a cofounder, so a common cause cofounder affects X and affects Y at the same time. Okay. But the difference here with the collider is that there are X and Y's who are actually cause something on the collider. Okay. So it's very important that, why we shouldn't consider them in our regressions. Okay, so is it clear why it is different with the cofounder? Because in a normal sense, you see the correlation always here, 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 and here. Okay, but yeah, you must have some knowledge about the possible causality links, and make sure that you shouldn't control for something that is not a cofounder. Okay, Any question here?
Actually, what could be an example of the last case? Can you give an example?
Yeah, you can think of. You know, the important thing is that there shouldn't be any link back here. Okay, so that's why I should think more. I hope it is right. So the tax rate for companies affects their revenue, and tax rate also affect the government spendings. Also, the revenue of companies affect the government spendings somehow. Okay, so as you see here, this government spending is something totally unrelated to our study. So if you happen to have this variable in your data set, you shouldn't necessarily control for that because you have it. Okay.
But once again, you could argue that government spending basically also influences the tax rate, because if they plan to spend a lot, they were likely to increase taxes.
Yes.
It's hard to find causal relationship.
Yes. Yeah. But I recommend you to come to some of our seminars. You can start this kind of arguments very fast. Yeah, that's the important thing. So you should make sure that there is no such a thing here or here. But yeah, I cannot find a better example right away. I hope I could give you some understanding of what's going on.
Yeah, thank you, clear.
Okay. Okay, cool. So let me just give you a summary of what we did. So so we have, and one in the beginnings we covered interventions, and then we say that data analysts usually wants to uncover the average treatment effect of those interventions. And and then we talked about exogenous and endogenous variables. So it should always think of an exogenous source of variation in X, which is a good thing that will be helpful for finding causal relationships. But on the other hand, the endogenous variation in X are bad because they confounds with the effect of the estimate that we want to measure. Okay, and then we also showed that the random assignment means that X is independent of the potential outcomes, and then it makes sure that the source of variation in X is exogenous. And then without random assignment, we need to isolate the exogenous source of variation in X, usually by conditioning on the endogenous source of variations. Okay. Any question on this summary? So is it clear that so at least in the case of a normal regression, you should always first create this causal map and find all the possible confounders, and you must always control for these confounders that you know, and you shouldn't control for these bad conditioners. So that's basically everything in a nutshell for just a normal regression. Yeah, So I have one slide on what I just said earlier. So yeah, it's very important to mind your language when you're talking about some causalities. So because when you talk about something affects something, it has always some policy implications. So if you think that storks bring babies, you should act on them for population policies. And also it's always nice to remember uncovering an effect is difficult. So always remember Democritus that I just mentioned in the beginning. And always please be critical when you hear things like X effects cause results in Y, okay? Because if something affects that, so it means that if you, for example, double the X, you should expect double the Y or something like that. And you should always ask if it makes sense at the end, okay? And yeah, if you always see that there was an experiment showing this, for example, this they found that having masks reduced the COVID or something, always think of what was their experiments. So did they actually put people in some places and then suddenly gave the mask away from them? And did they really did a random assignment in doing this experiment or not? And then you always also see that there was a regression going on and something like that, always think of some confounders that they didn't control for. Okay, that's the way to be critical about the causal relationships. And yeah, but at the end, yeah, being too much perfectionist won't help because every study is imperfect. So, I mean, if you also go to Journal of Finance, which is the best we could have, yeah, you can still. So I remember in our second year courses, we were forced to just discussing this JF papers. So the professors gave us some papers in the Journal of Finance, which is basically the best we could have. We still, our job was to find some problems in their causal arguments. So yeah, exactly. So some studies are better than the others, but at the end, it's very important to see how they search for these problems of showing the causality links. Okay. Yeah, so I think I'm finished for today. Is there any question? Okay. Yeah. So yeah, I hope I see you on Monday again with our nice guest lecturer. I think they are also searching for some people who could do some textual analysis for their asset management industry. And if you are interested, please be there and be active during the course.
Yeah, so I think you should send an email to all, because if external speakers come here, yeah, we would like to show a large enough group, and it would be a shame if too few come. Yeah, so
Exactly.